Good evening, everyone. I'm going to read now the chapter 4 from the book on Fundus Autofluorescence by J V Forrester. It's chapter 4, page number 38. Lipofuscin and autofluorescence in experimental animal models. Fundus autofluorescence imaging is increasingly being used in ophthalmic practice to aid in the diagnosis and monitoring of patients with a variety of retinal disorders. Thus, it is particularly important to understand molecular and cellular sources of fundus autofluorescence. Only with such an understanding can doctors interpret and judge the significance of fundus autofluorescence changes in various pathological conditions. However, it is very difficult to obtain such information from human studies. In this context, experimental animal studies may have great additional value. Improvements in vivo fundus autofluorescence imaging techniques and the development of various animal models of disease enable us to carry out direct clinico-pathological correlations as well as dissect the detailed mechanisms of lipofuscin formation. The value of experimental animal models. Experimental animal studies are valuable because they allow us to investigate the clinico-pathological correlation of fundus autofluorescence and the pathological changes related to various autofluorescence patterns. Such information is critical for clinicians to correctly interpret autofluorescence images. Although a variety of animal models representing different types of human retinal diseases have been developed over the years, only a few autofluorescence clinico-pathological studies have been published, including a study from the author's laboratory in normal-aged mice. Another important use of experimental animal studies is to investigate the mechanisms of lipofuscin formation. Studies in the field have identified a few important factors involved in vivo lipofuscin formation, including the RPE65 gene and vitamin A. In addition, animal studies are of great value for testing the effectiveness of various treatments, particularly those targeting the formation of the lipofuscin. Imaging techniques. In vivo imaging, currently, confocal scanning laser ophthalmoscopy (CSLO) is the most widely used technique to image fundus autofluorescence in vivo. Because all commercial confocal scanning laser ophthalmoscopes are designed to image the human fundus, slight modifications such as the use of spatial lenses are needed to image rat or mouse retina. Various groups have used this system to image the rodent fundus. In the author's laboratory, a custom-built CSLO scanning laser ophthalmoscope, that is confocal, is used in experimental animal studies. To be able to image the mouse fundus, we use a plus 25 diopter lens placed 1 centimeter in front of the mouse cornea to further focus the laser beam, as it is human for mice study. Plus 25 diopter lens is used here. In addition, a mouse hard contact lens is also used to prevent tear evaporation and keep the eyelids open. We are able to image a 43 by 32 degrees field of mouse fundus. This in vivo imaging technique is non-invasive and therefore changes in the fundus can be followed up at different stages of disease in the same animal. Ex vivo imaging. As with human samples, lipofuscin in animal tissues can be extracted and examined in vitro by various techniques. Traditionally, tissue autofluorescence has been imaged in situ with the use of various fluorescence microscopes. Fluorescence microscopy is still a simple, straightforward, and useful technique to detect lipofuscin. Currently, however, more advanced and sophisticated technologies are used to quantify lipofuscin content and examine the detailed fluorescence emission spectra of lipofuscin. Bui and colleagues, BUI. Bui and colleagues used a fluorescence microplate reader to examine the fluorescence emission spectra of RPE choroid and retina explants. In their system, fresh samples were placed side up in a modified C84 well microplate. Emission spectra were measured following excitation at 420 nanometer using the top read mode. This technique allows one to measure the emission spectra as well as the relative fluorescent units of RPE choroid and retina explants. In the author's laboratory, the lambda mode of a confocal scanning laser microscope is used to image fluorescence emission spectra of mouse, RPE choroid, and retina explants. This technique has several advantages. 1. Samples can be excited with different lasers and the characteristics of emission spectra excited by the different lasers can be studied. 2. It detects the emission spectra of individual cells or regions but not the whole tissue, allowing comparisons of the emission spectra of different cells of different regions. 3. The fluorescent intensity of different tissues or different regions can be quantitatively recorded and analyzed. The lambda mode of the LSM510 Meta confocal microscope is designed to separate the fluorochromes with widely overlapping emission spectra or fluorochromes that are excited by the same laser. It is widely used to eliminate sample background autofluorescence with the meta scanning systems. The emission fingerprints of each fluorochrome can be collected and a spectral database can be built. It is therefore an ideal means of studying the fluorescence spectra. Now figure 4.1, autofluorescence emission spectra of a mouse RPE cell. The RPE flat mount was prepared from a 2-year-old C57BL/S6 mouse and examined with the use of LSM510 Meta confocal microscope lambda model. The sample was excited with a 458 nanometer helium neon laser and the emission signals were collected from 460 to 697 nanometer. A. Emission spectra database of the RPE cell. B. Autofluorescence intensity at different emission wavelengths extracted from the database in A. So it is therefore an ideal means of studying the fluorescence spectra of lipofuscin. With a metascanning mode, emission signals are detected by a polychromatic 32-channel detector, which allows the fast acquisition of lambda stacks. Samples can be excited with lasers at 448 nanometer, 477 nanometer, 488 nanometer, 514 nanometer, 543 nanometer, and 633 nanometer separately. For each excitation, the emission spectral range for lambda stack acquisition can be controlled as required, and the upper limit is 790 nanometer. For all lambda acquisitions, the pinhole needs to be set to 1 array unit and the scanning speed set to 6. To be able to compare the emission fingerprints acquired from different cells or tissues, the configuration including the detector gain, amplifier offset, and amplifier gain should not be changed during the process of acquisition. An example of mouse RPE lipofuscin emission spectra excited by 458 nanometer is shown in figure 4.1. Clinicopathological correlations of fundus autofluorescence in experimental animals. Although various pathological studies in retinal RPE lipofuscin have been carried out in post-mortem human eyes over the past decade, obviously no living human being is going to sacrifice his or her eye for the histopathological examination of his or her eye just for the experimental purpose. So the animal studies are, these things are studied in animal models and the post-mortem human eyes. To date, the clinicopathological correlation of fundus autofluorescence findings in the majority of retinal diseases is still largely unknown. Fundus autofluorescence in the normal mouse. To be able to understand the fundus autofluorescence changes in various animal models of diseases of the posterior segment, the characteristics of the fundus autofluorescence in healthy control animals need to be established. We have investigated the fundus autofluorescence in normal C56BL/6 mice of different ages. The overall fundus autofluorescence increased with age in normal C57BL/6 mice by confocal scanning laser ophthalmoscope. 1. Increasingly strong autofluorescence signals were observed with age in the neuroretina and subretinal RPE layer. Unlike fundus autofluorescence detected in normal human subjects, fundus autofluorescence appeared as discrete foci or foci distributed throughout the retina. Most of the autofluorescence signals in the neuroretina were distributed around retinal vessels. Immunohistological studies of retinal RPE choroidal flat mounts indicated that most of the autofluorescence signals derived from IBA1 plus perivascular and subretinal microglia, and some derived from the RPE cells. Figure 4.2, fundus autofluorescence in a normal aged mouse. Figure A, fundus autofluorescence in an 18-month-old C57BL/6 mouse. B, confocal microscopy of RPE flat mounts of the same mouse reveals many autofluorescent cells located on the surface of the RPE cells. The autofluorescent cells on the RPE cell surface stain positive for the microglia marker IBA1. So this figure showing the autofluorescence coming from the RPE cells and what microglial cells. Now figure 4.3, lipofuscin in subretinal microglia and RPE cells. Figure A, subretinal microglia with lipofuscin. Figure A, there is a subretinal microglia with lipofuscin. Insert emission spectra of subretinal microglial lipofuscin excited with 488 nanometer. And B, RPE cell with lipofuscin. Figure B shows RPE with lipofuscin. Insert emission spectra of RPE cell lipofuscin excited with 488 nanometer. These graphical presentations, I'm not going to just go in detail about that because it's not very clinically significant. We just want to know that from where the autofluorescence is coming. Here it's coming from the microglial cells, the lipofuscin present in the microglia and lipofuscin present in the retinal pigment epithelial cells. You just remember the summary and the inference of these experiments, conclusion of these experiments. You don't need to go in detail if you are interested. I'm just reading so that I shouldn't miss any point. So you will feel fulfilled that yes, we have gone through the book and we have gone through the book through these videos. And that's why I'm being very fast. If you want me to slow down, you can just slow down the speed. There is an option here on YouTube. The number of subretinal microglia and the amount of intracellular lipofuscin increased with age. Transmission electron microscopy (TEM) revealed many lipofuscin granules in the cytoplasm of subretinal microglia. Emission spectra detected by the meta-scanning mode of the confocal microscope indicated that the spectra of the lipofuscin in the subretinal microglia and the RP cells were the same, suggesting that they may have the same chemical components. So they are confirming the findings. Transmission electron microscopy revealing the lipofuscin granules in the cytoplasm and the subretinal microglia, and also the emission spectra, confocal microscopy, indicating what? That the lipofuscin present in the subretinal microglia and the RPE cells, these are same. These lipofuscin's composition is same. They have the same chemical components. Fundus autofluorescence in mouse model of disease. CCR2, CCL2 knockout mice. What is the CCR2 and CCL2 and what is knockout mice? Mice different in either monocyte chemoattractant protein 1, CCL2, chemoattractant protein 1, monocyte chemoattractant protein 1, CCL2, also known as MCP1, or its cognate CC chemokine receptor 2, CCR2, develop the cardinal fundus features observed in patients with age-related maculopathy (ARM) or age-related macular degeneration. These include drusen, geographic atrophy, and choroidal neovascularization. Both strains of mice develop drusen-like changes at the age of 9 months. By 16 months, geographic atrophy can be observed. Choroidal neovascularization can be detected in 1/4 of the CCL2 negative and CCR2 negative. Negative means these genes are absent. Knockout means absent. Mice at the age of 18 months. Now, how they specifically remove certain genes from the animals or from the human beings in the experiments, that I don't know, and it's not even given over here. So, such mice are therefore considered good models for ARM AMD. Clinically, we observed drusen-like and geographic atrophy-like changes in our CCR2 and CCL2 knockout mice purchased from the Jackson laboratory, but no subretinal neovascularization. Fundus autofluorescence imaging using confocal scanning laser ophthalmoscopy indicated many more autofluorescent foci present in CCL2 or CCR2 deficient mice compared to age-matched wild-type control mice. Ex vivo confocal imaging of retinal flat mounts from this animal model revealed many perivascular and subretinal IBA plus microglia with autofluorescent lipofuscin, similar to those seen in normal aged mice but significantly higher numbers. Now CFH knockout mice. Now what is CFH? Now CFH is what? Complement factor H. Genetic studies have revealed a strong association between a broad range of age-related macular degeneration phenotypes and variants in the gene encoding complement factor H, CFH gene. CFH is the major plasma protein that exclusively regulates the alternative pathway of complement activation. Complement factor H protein has been detected in drusen, the pathogenic hallmark of AMD. Drusen is the pathogenic hallmark of AMD, age-related macular degeneration. CFH deficient mice, that is complement factor H deficient mice, exhibit significantly reduced rod response on electroretinography compared to age-matched controls. Fundus autofluorescence of these mice by scanning laser ophthalmoscopy revealed an increase in autofluorescent subretinal deposits similar to those observed in CCR2 and CCL2 deficient mice. More recently, using ex vivo confocal microscopy of retinal and RPE or choroidal flat mounts, we showed that majority of the autofluorescent signals were from the subretinal microglia. Majority of the signals, autofluorescent signals from the subretinal microglia in the animal models. And we have seen that these CCR2, CCL2 and CFH gene absence in the mice, how they are related to these AMD kind of changes. So figure 4.4, mouse fundus autofluorescence. Figure A, fundus autofluorescence of an 18-month-old C57BL6 mouse. B, but fundus autofluorescence of an 18-month-old CCL2 knockout mouse. So, fundus autofluorescence in experimental autoimmune uveitis. Clinical studies have shown altered autofluorescence in various chorioretinal inflammatory diseases. Inflammation may alter RPE and photoreceptor cell function and subsequently affect the production of autofluorescent molecules. Furthermore, inflammatory cells, in particular macrophages, may contain autofluorescent materials as a result of active phagocytosis of oxidized substances at the site of inflammation. It is therefore important to understand the correlation between autofluorescent patterns and pathological changes in chorioretinal inflammation. We have carried out clinical pathological studies in a mouse model, experimental autoimmune uveitis. Experimental autoimmune uveitis. It was induced by immunizing C57BL/6 mice with human interphotoreceptor retinoid binding protein. So what they are doing here, they are inducing the autoimmune uveitis in mice by injecting this human interphotoreceptor retinoid binding protein. So sad that these animals, they don't even know that they are going to lose their eye. So just for for the benefit of human beings, I don't know how much it is justified, and I think it is absolutely not justified, because these are innocent animals. What they have done nothing wrong to us, but it's very cruel. Many of that's why I try to be very healthy, and I just feel like not falling sick or ill. So I shouldn't be dependent on such medicines which come from harming so many animals through the experimental phases they have gone. and even later on human beings. So I somehow don't feel like, I take medicines and thankfully I don't fall sick often. But I feel, these people without their consent are harmed for the benefit of the people. And you should be grateful, and actually, I think there should be some opposition. Yeah, this is what I feel. Such cruel experiments, I don't like. Somehow, I don't like. With human interphotoreceptor retinol binding protein IRBP peptide, in this autoimmune uveitis model, experimental autoimmune uveitis model, retinal inflammation starts at day 10 to 12 post immunization PI, peaks at day 20-25 PI, and resolves, PI means post immunization, and resolves at about day 30. Fundus autofluorescence was imaged at disease initiation day 12 PI, that is post immunization peak, and resolution stages, means 3 stages fundus autofluorescence, just to see the fundus autofluorescence, what happens to the fundus autofluorescence in inflammatory conditions in human beings. So they studied first in mice. So they studied it by inducing this disease in healthy mice. So sad. Then they took the fundus autograph images and they studied them at 3 stages: day 25, resolution day 35, and day 12 also. At day 12 PI, when inflammation was very mild and localized in the optic disc or venule fragments, fundus autofluorescence was largely normal. Neither an increased nor a decreased autofluorescence signal was observed in inflamed retina areas compared to non-inflamed ones. As inflammation progressed, increased autofluorescence signals began to appear in the areas of the inflammation at the peak stage of this experimental autoimmune uveitis. Autofluorescence signals appeared as discrete small dots of increased autofluorescence surrounding inflamed vessels. At the late stage of inflammation, day 35 PI, post-immunization, disease resolution stage, a massive destruction of photoreceptor cells was observed. Highly increased autofluorescence signals were seen throughout the retina. Ex vivo confocal microscopy of retinal RPE choroidal flat mounts revealed many autofluorescent cells at the site of inflammation, particularly in the area of retinal around the inflamed vessel segments. Immunofluorescence studies indicated that these autofluorescent cells were F4/80 plus macrophages. Now the pictures, we'll see some pictures here about the fundus autofluorescence in experimental autoimmune uveitis. What they found here, it's like a summary only. Figure 4.5. Autofluorescence cells in the subretinal space. The retinal flat mount was prepared from 12-month-old CFH knockout mouse and imaged by a confocal microscope. That is the first one, CFH knockout mouse, that is the figure 4.5 here, earlier experiment. The image was taken from the photoreceptor side of the retinal flat mount. Many AF cells are seen within the outer segment of the photoreceptor cells. So when CFH knockout mouse, when the CFH gene was deleted from the mice, what happened? They saw the increase in the autofluorescence coming from the subretinal space, from the and especially from these outer segment of photoreceptor cells. From there, the autofluorescence was coming. Now, figure 4.6, fundus autofluorescence in peak stage uh, experimental autoimmune uveitis A. Fundus image taken from a day 22 post-immunization EAU mouse showing massive inflammation in the retinal venules. Arrow. Fundus photograph showing the inflammation. There is a white area around the vessels, that is the inflamed area, and engorgement of the venules seen here with little bit of tortuosity. Then B, Fundus autofluorescence image showing increased autofluorescence signals in the optic disc and the infrared venules. So they saw increase in the autofluorescence signals coming from these inflamed areas, that is perivascular area and around the optic disc. That is figure 4.6. These figures and this conclusion, it's like summarization of this experiment. Figure 4.7, fundus autofluorescence in late stage of experimental autoimmune uveitis. Images were taken from a day 35 post-immunization EAU mouse. A, fundus image showing atrophic retina and inflamed venule segment. Arrow. B, figure B, many small foci or foci of increased autofluorescence distribute throughout the retina, with more in the perivascular area. Arrow. The autofluorescent background is lower than that of the peak stage experimental autoimmune uveitis retina. Experimental animal studies to dissect the mechanism of lipofuscin formation. Studies on the mechanism of lipofuscin formation in the eye have exclusively focused on the RPE cells. It is believed that the formation of lipofuscin in RPE cells involves the visual cycle between the RPE and photoreceptors and the reduced lysosomal function in the RPE cells. In addition to other mechanisms, we have already seen that lipofuscin, how it is formed. Three things, that was lipofuscin dysfunction, then autophagy, and cellular stress, LAC, lack. So now this lysosomal dysfunction, then the visual cycle products here. The visual cycle is tightly regulated cycle in which retinoid vitamin A is required for the visual cycle. Dark adaptation, dark adaptation, light adaptation. Visual cycle is tightly regulated cycle in which retinoid vitamin A moves back and forth from the RPE cells to photoreceptor outer segments through the interphotoreceptor matrix and is strongly retained in this loop. I'll be talking about the visual cycle later on, but in just 15 minutes, 15 to 20 minutes, I'll read from one of the books. I forgot the name of it. I'll read from it so to have better understanding of the visual cycle. Honestly, in many books it's not given to satisfy my doubts about the visual cycle, but still whatever is given in the book I'll read, and it's given in more detail in one book. I forgot its name. The visual cycle is a tightly regulated cycle in which the retinoid vitamin A moves back and forth from the RPE cell. So where the visual cycle takes place, it takes place in the rods and the cones. Cones are more active. More active means they're responsible for the light vision, and dark adaptation means in the darkness we see because because of the chemical changes predominantly taking place in the rods, and why so that we'll see in detail later on. But for this cycle, vitamin A is required, and this cycle not only takes place in the rods and cones, that is for which are responsible for the night vision and the light vision respectively, but the regeneration of these products, it they are processed through the RPE, the diffuse from the outer segments. These outer segments are taken up by the retinal pigment epithelium because it has the macrophage function, and that's why it's very important not just to read the clinically pathological conditions but also read about the physiology and anatomy, so we can have the better idea what's going on exactly. So these outer segments, where exactly they are outer segments near the corona. So outer segments near the RPE, these are taken up by the RPEs because they have the macrophage function also, along with the absorption of the light, melanin, to sharpen the image on the retina. The visual cycle is tightly regulated cycle in which retinoid moves back and forth from RPE cells to photoreceptor outer segments through the interphotoreceptor matrix. So from RPE, then it will be recycled, this vitamin A, this all transretinal to 11C's retinal, and it will move back to the outer photoreceptors again, outer photoreceptor segments, and then visual cycle, it continues like this. Now some of the products will not be digested, especially those subjected to the oxidative stress, peroxidase and free radicals, they are not digested by these lysosomes in the RPE, and they will be retained there and there will be this lipofuscin formation. And one of the precursors or components that is widely studied, that we have seen, that is pyridinium bis retinoid, formed in the outer photoreceptor segment, and it has got the fluorescence property. Then it forms that A2E component, which is a major component and widely, not major as such, but widely studied component of the lipofuscin. So these are the fluorophores this is one of the fluorophores in the lipofuscin. There are many other because it has got the wide spectrum of emission range. And why? So because it has not just one fluorophore but multiple fluorophores. That was the conclusion of the studies. But they have mentioned only A2E here in this book. Then retinoid is released from the bloodstream to RPE cells. It is released from retinoid. It is released from bloodstream to the RPE cells. With the light illumination, retinoid moves from the retina to RPE cells. With the dark adaptation, the process is reversed. That is, night, it is flowing from the blood vessels to the RPE. In the dark, the process is reversed. It will flow from the photoreceptors to the. It will flow from the RPE to the blood. So, substantial evidence indicates that vitamin A derivatives, retinoids, are required for RPE lipofuscin formation. In normal rat retinas, age-related lipofuscin accumulation occurs in RPE, and vitamin A deficiency has been shown to reduce the RPE lipofuscin. So, they have seen in normal rat retinas, what they have seen, age-related lipofuscin accumulation occurs in RPE cells. They saw that when there is increasing age, there is lipofuscin accumulation in the lysosomes of the RPE, and then when there was vitamin E deficiency in such rats, it was shown that it reduces this RPE lipofuscin formation. In the Royal College of Surgeons (RCS) rat, a strain with an inherited retinal dystrophy, lipofuscin-like autofluorescence develops in the degenerating photoreceptor cells, and vitamin A deficiency substantially reduces the autofluorescence associated with degenerating photoreceptor cells. So in degenerative retinal conditions also there is inflammation going on. So there is going to be microglia, there are going to be lysosome autophagy happening. So these lipofuscin formation increasing the autofluorescence over there, that's the mechanism that we have known. And then if there is vitamin A deficiency, these visual cycle products won't be formed, and this autophagy will be reduced, and hence there is a reduction in the lipofuscin and reduction in the fundus autofluorescence in such conditions. Then furthermore, a vitamin A dependent fluorophore was isolated from these retinas. Vitamin A dependent fluorophore was isolated from these retinas with the use of a thin layer chromatography TLC. However, this fluorophore differs in fluorescence intensity and mobility in TLC from that aged RPE cells of the retina, from that of the aged RPE cells of normal rats. It appears that the fluorophore generated in the photoreceptor cells must undergo chemical modifications once it has been taken up by the RPE. The requirement of vitamin A for lipofuscin formation is further supported by a study in which lipofuscin was induced in RPE cells by intravitreal injection of the lysosomal protease inhibitor leupeptin. Leupeptin is lysosomal protease. Lysosome has various degrading enzymes, protease here. So this leupeptin injection, which is what? This is lysosome protease inhibitor, leupeptin. So intravitreal injection of this leupeptin was given in the rats, and rapid accumulation of inclusions with lipofuscin like autofluorescence in the RPE of albino rats. However, in vitamin A deprived animals, similar inclusions formed in response to leupeptin treatment, but they did not become autofluorescent. It appears likely that retinoids are directly incorporated into these inclusions in another animal study in which all transretinol has labeled with H3 and injected into rats that were treated with an intravitreal injection of leupeptin. The radio label in the RPE was primarily associated with the leupeptin-induced inclusion bodies. The label was also present in the photoreceptor outer segments. The localization of vitamin A to the leucopeptine-induced inclusions in the RP strongly suggests that vitamin A is covalently bound to the outer segment proteins that have been phagocytosed by the RPE but remains undegraded as a result of protease inhibition. Vitamin A is not likely to bound to the Steve base linkage since retinal Steve base compounds do not exhibit lipofluorescence. The importance of a normal visual cycle in the formation of the lipofuscin is also supported by studies in RPE65 knockout mice. So what they are saying that vitamin A, they are studying the lysosomal enzyme. Now lysosomal enzyme is not working here because we injected this leucopeptine, and there was what, when the leucopeptine was injected, there was increase in the autofluorescence because obviously this leucopeptine, this lysosomal dysfunction is one of the mechanisms of the lipofuscin formation, and if we are blocking that thing with the leucopeptine injection, means there is decrease in the lipofuscin formation. And also vitamin A deprived animals also there was decrease in the lipofuscin formation. So for that they use this radio labeled H3 to see what was happening in the fundus autofluorescence. The importance of normal visual cycle in the formation of the lipofuscin is also supported by the studies in RPE65 knockout mice. RPE65 is essential in the operation of the visual cycle and functions as a chaperone for all transretinal esters. The substrates for chaperone means the supervising molecules. During the visual cycle, the visual pigment chromophore 11-cis retinal is photoisomerized to all the trans configuration and then enzymatically isomerized to the 11-cis isomer. So RPE is responsible for what? RPE65, it is responsible conversion of the this gene and these proteins, group of proteins responsible for the conversion of all transretinal esters to the 11-cis retinal. 11-cis retinal is photoisomerized to the all trans configuration and then enzyme reisomerized to all to the 11-cis isomer. RP65 proteins are essential for the isomerization of all trans to 11-cis retinal. Mice with RP65 deficiency, RPE65 negative. No, means these genes are deleted. I don't know how they delete and how they just make these spaces to exist. Specifically deleting certain genes and targeting certain genes for experimental purpose. I don't know. I have a lot of interest, but I don't want to. I'll never dare to bully any animal like this. Never. Accumulate almost no lipofuscin in RPE cells, and RPE65 plus minus gene means one gene is present, another gene is not there in the pair of RPE65. Mice also have significantly reduced accumulation of the lipofuscin fluorophores in the RPE cells. Further experiments in RPE65 knockout mice with protease inhibitor leucopeptine treatment showed that although lipofuscin-like inclusions were observed in both WT and RPE65 knockout mice, only the inclusion from WT-RPE and not RPE65 negative RPE autofluorescence. These observations suggest that the formation of the RPE lipofuscin fluorophores is almost completely dependent on a normal visual cycle. So they understood the retinoid dependent lipofuscin fluorophore. Retinoid dependent means that is coming from the visual cycle. For that they use this leucopeptine injection, vitamin A deficient animal models, and also RP65 knockout mice. Combine these results and interpreted that this lipofuscin fluorophore is one fluorophore. It is completely dependent on the normal visual cycle. In line with these experimental studies in mice, lack of autofluorescence in patients with early onset severe retinal rod cone dystrophy has been observed. Early onset severe rod cone dystrophy is believed to be associated with the RP65 mutation. When there is RP65 mutation, what happens? There is early onset severe rod cone dystrophy because of RP65 mutation, not deletion here. The fact that leucopeptine treatment induces lipofuscin-like inclusions suggests that the loss of lysosomal functions is also responsible for the formation of the lipofuscin. The inclusions are derived from photoreceptor outer segments, which are normally phagocytosed and degraded by the RPE. A normal lysosomal function is essential for the degradation of the phagocytosed materials. Obviously, the tripeptide leuglygly, which is similar to glycine, leucine, glycine, which is similar to leucopeptine, except that it does not inhibit proteolysis, has no effect on RPE autofluorescent content. Likewise, netilmicin, a purported inhibitor of lysosomal phospholipases, does not increase autofluorescence in the RPE. They are just studying other lysosomal enzymes also, whether their absence, presence, how they affect the lipofuscin formation. So it was protease inhibitor enzymes which caused accumulation of the lipofuscin in the lysosomes of the RPE, but there were other these enzymes uh, when were deficient or when there was deficiency of them, they have no effect on the fundus autofluorescence and hence no effect on the lipofuscin formation. In summary, experimental studies on the formation of the lipofuscin in RPE cells suggest that the loss of lysosomal function is essential for the formation of the lipofuscin in inclusions, whereas normal visual cycle is required for lipofuscin formation. Testing anti-lipofuscin compounds in animal models. Increasing knowledge regarding the mechanism of lipofuscin formation will enable the development of the anti-lipofuscin drugs, which could be of benefit in various retinal degenerative diseases, as summarized above. Inhibiting visual cycle function with small molecules has been to be an effective approach to prevent lipofuscin formation. Various animal models have been used to test the effectiveness of compounds designed to inhibit lipofuscin formation. The effect of isotretinoin, Accutane. Isotretinoin, remember, Accutane. Now we know the lipofuscin formation. Now why we studied the lipofuscin, how it is formed, because we want to block the stages, because this lipofuscin, it is in the previous second chapter we have studied that it is cytotoxic, and then these fluorophore components, they have cytotoxic effects, they activate the complement and hence inflammatory and cause inflammation, cytolysis, apoptosis, that we have seen in chapter 1, 2 and also 3. Also they increase the expression of the VEGF uh, on the RPE cells, so responsible for the neovascularization. So if we block this lipofuscin formation, obviously we are going to decrease the inflammation or these degenerative changes taking place in the fundus, leading to increased autofluorescence. So this isotretinoin, Accutane, which has been shown to slow the synthesis of 11-cis retinaldehyde and regeneration of rhodopsin. So it slows down what? It slows down the synthesis of 11-cis retinaldehyde and it slows down hence the regeneration of the rhodopsin. It slows down, has been tested in ABCA4 negative knockout mice. Now ABCA4 gene, it is not present. Now it is deleted in these experimental mice. And what is the effect of this isotretinoin Accutane? What it does, it decreases the synthesis of 11-cis retinaldehyde and regeneration of the rhodopsin. A mouse model of Stargardt's disease. Mouse model of Stargardt's disease, ABCA4 knockout gene, that is seen in case of the related to the Stargardt's disease. What is Stargardt's disease and all, we'll see that later on because then it will be too long. Fenretinide N4-hydroxy phenylretinamide HPR potently and reversibly reduces serum retinol. Administration of HPR to ABCA4 negative knockout mice caused immediate dose-dependent reductions in the serum retinol and retinol binding protein. Decrease in the this isotretinoid administration. What it did, it decreased the serum retinol and retinol binding protein. Chronic administration can produce commensurate reduction in visual cyclotretinoids and arrest accumulation of the A2E and lipofuscin autofluorescence in RPE cells. Physiologically, HPR treatment causes modest delays in dark adaptation, chromophore regeneration kinetics, light sensitivity of photoreceptors, and phototransduction processes are normal. HRP could be a novel therapeutic approach with first was isotretinoin, second is fenretinide. Isotretinoin, what it does, it reduces the synthesis of 11-cis retinaldehyde and regeneration of the rhodopsin in ABCA4 knockout mice, both the genes related. Mouse model of Stargardt's disease. Then second thing is fenretinide. Fenretinide is HPR. HPR is what? 4-hydroxyphenyl retinamide. It reversibly reduces the serum retinol. Reversible reduction of the serum retinol, and This administration of the fenretinide in ABCA4 knockout mice caused immediate dose-dependent reduction in serum retinol and retinol binding protein. Okay, retinol levels decreased. Chronic administration can produce commensurate reductions in the visual cycle retinoids and arrest accumulation of the A2E and lipofuscin autofluorescence in the RPE cells. Physiologically, so what fenretinide does, it causes reduction in the serum retinol and retinol binding protein in ABCA4 knockout mice in Stargardt disease, and it arrests the accumulation of the A2E and lipofuscin autofluorescence in the RPE cell. Physiologically, HPR treatment, that is fenretinide treatment, causes modest delays in the dark adaptation. Obviously, visual cycle is affected a little bit. Dark adaptation part of the visual cycle is affected, and chromophore regeneration kinetics, light sensitivity, photoreceptors, and phototransduction processes are normal. HRP could be a novel therapeutic approach with the potential to halt the accumulation of lipofuscin. HRP means fenretinide of lipofuscin fluorophores in the eye. In this regard, a phase 2 randomized double-masked placebo-controlled multicenter study using fenretinide is currently underway. Non-retinoid isoprenoid compounds have been shown to serve as antagonists of RP65. Now, non-retinoid isoprenoid compounds, which are non-retinoid, RPE65, antagonists of the RP65. The RP65 antagonists block the generation of the 11-cis retinal, the chromophore of rhodopsin. Chronic treatment of a mouse model of Stargardt disease with RP65 antagonist abolished the formation of the A2E. So, Stargardt disease, ABCA4 knockout mice. These are the mice with Stargardt disease. If we give them RP65 antagonists, then what happened? There was blockage of the 11 trans retinal conversion to 11 cis retinal, and it abolished the formation of the A2E, means it improved the condition. What is that RP65 antagonist? It is isoprenoid compound, that is non-retinoid isoprenoid compound. Thus, RP65 is also on the rate-limiting pathway of A2E formation. These non-toxic isoprenoid RP65 antagonists are candidates for treating forms of macular degeneration in which lipofuscin accumulation is an important risk factor. These antagonists will also be used to probe the molecular function of RPE in vision. So, what's the summary of this chapter and these experiments? Although autofluorescence imaging has been used in the clinic for almost a decade, our understanding of fundus autofluorescence is still limited. Animal models are important tools for gaining insight into pathological changes and their correlation to observed fundus autofluorescence changes and the mechanisms underlying the formation of the lipofuscin. They are also valuable for the development of effective drugs targeting the lipofuscin formation with the goal of preventing retinal degeneration. Studies conducted so far on the mechanisms of lipofuscin formation have revealed many important molecules, and consequently, new treatment approaches are being developed. The study of clinical pathological correlations of fundus autofluorescence has just begun. It has been demonstrated that other cells beside RP cells may produce lipofuscin. Further work, in particular using different animal models of disease, is needed to understand the abnormalities in the distribution of fundus autofluorescence observed in different retinal diseases, as well as their significance. It should be remembered, however, that any observations made in animal models should subsequently be validated clinically in human beings. So that was the summary. Summary is what notes I'm going to make on this, but notes will take like 15-20 minutes on this, because this chapter is really good, because actually why we are studying this lipofuscin formation and where we can halt this process to reduce the inflammation and lipofuscin accumulation seen in the Stargardt is age-related macular degenerative changes like ARMD and Stargardt disease. So how we can just reduce that thing, for that this chapter is very important. And they have discovered that other cells, not just RPE, also accumulate the lipofuscin and also responsible for the autofluorescence, fundus autofluorescence, that the studies are still in experimental process. They are still being studied. So for notes, I'm going to make another video. Here I'll stop, but I'm feeling extremely bad while reading all this. How many animals are sacrificed for these kind of experiments? I don't know, like some non-violent. There should be some non-violent way to study such things, I feel. Bye everyone. You can just carry on to my next video, that is on the notes part. You can just skip this video and just directly jump onto the notes part. Bye everyone.